very much for having me. I'm very excited to be here. So let me move over here so I'm a little bit more central. Let me, before I begin, just say that please feel free to interrupt at any time, ask questions. I will pause for questions, but if I'm not pausing frequently enough, please do stop me and flag me down. Okay, all right, so I'm going to be talking about three things. And so first I'm going to give a very brief introduction to topic models if you haven't heard about those before. Then I'm going to sort of talk about how topic models go bad and what are the problems that are sometimes associated with topic models, and then what can we do to fix those problems. Okay, first, what are topic models? So imagine that you have a very large collection of documents, say like a decade of newspaper articles. How can you get an idea of what's going on inside this collection without sitting down and reading all of them? And a topic modeling approach is one way to tackle this problem. You can sort of get an idea of the broad themes that are happening in your collection of documents. And the nice thing about this is that it's an unsupervised approach. You don't have to have any laborious hand annotation. You don't have to have any systematic annotation of your corpus ahead of time. You have the data, it sort of tells you what's there. And so at a very high level, topic modeling works as follows. You have as input a bunch of documents, and these documents contain some words, and as output, you get a bunch of topics, which is why these are called topic models. And these topics that you get out have some sort of broad semantic coherence. And so, for example, if you use the New York Times from the 1990s, you get topics like a technology topic, a business topic, and an arts topic. Yep?
So actually, if you do it to the Times, I imagine you get things like sports, New York murders, murders in other countries and stuff like that. So at the first, just at the start, do you ask, can we tell sports from fashion, from?
Right, and so these are not, so first you have to say how many topics you want the algorithm to find. And so this is one of the inputs in addition to the corpus, and so depending on how many topics you ask it to find, it will do either more granular or broader topics. And so it will discover what it discovers, and so these things might make sense to you, and usually they do. And so, for example, if you ask it to find 50 topics, you get things that look like this, which do sort of match up with our intuitions about what arts, business, and technology might look like. Does that answer your question?
If you had said, if you asked me for 3, you get this, then it would have answered my question, but you did say 50.
Yes, and so these are 3 of 50, and so because I can't show 50 to you all at once. And so if you asked for 3, you would probably get something like New York, world, and national. So like.
Are you only working with the news articles?
No. So so we exclude editorials, but this doesn't. So we exclude editorials and obituaries, but everything else is fair game. So this includes the art section and lifestyles and things like that. Other questions? Okay. All right. So this is the output that you get, and so you have a bunch of topics. In addition, you also get an association of topics to the documents. And so, so one document might be called Red Light, Green Light, a two-tone LED to simplify screens. And that's all about technology. So it's all the way over here in this corner of a triangle. And so this is a triangle representing the 3 topics I just showed you. As you move over more towards the business topic, you get documents like the 3 big internet portals begin to distinguish among themselves as online shopping malls, which is a mixture of both the technology topic and the business topic. And then as you move down in the triangle, you get things like forget the bootleg, just download the movie legally, which is a combination of the arts, the business, and the technology topic all at once. And so this is sort of the cartoonish version of what a topic model gives you. It tells you what's in your corpus. You have a bunch of these topics, and here are the association of the documents to these topics. Questions so far? Okay. So the takeaway from topic models, topic modeling is an unsupervised approach for finding out what's going on in a corpus. You don't really need to give it any a priori information. It just discovers what's there using a process of statistical inference. And the topics that you find make sense because of the way that language is used. Because we use topics coherently and put them together in ways that sort of duplicate across many documents, we discover topics that make sense using this statistical analysis. And I'm going to focus on something called latent Dirichlet allocation. I'll talk a little bit more about the details later, but it's basically a Bayesian version of PLSI, latent semantics indexing, if you've heard of that. And so this might connect to the things that you've seen before. And just to give you sort of a flavor of why other people have been interested in topic models, within sort of the text world, people have used it for distant reading. So you have a large collection of text, and this is a way for you to sort of get an idea of what's going on. And so Matt Yockers at Stanford has done this for English novels. Bob Nelson at Virginia has done this for Civil War era newspapers. Some very interesting stuff that sort of allows you to discover what's going on in a large corpus very quickly. And then beyond text, people have been doing it for music analysis, for visual analysis, for social network analysis. It's been applied to a variety of places. But we're going to be focusing on text here. OK, so now where topic models go bad. All right, so we've talked about how you fit topic models, how you discover topic models from a large collection of data, but how do you evaluate them? So typically what's done in the literature is that you fit a bunch of topic models, and then you have some data that you didn't allow the model to see before, and you ask it to predict how well it could generate these new documents. And so you get something called a held out log likelihood. I won't go into the details about that. But this is basically just measuring the predictive power of the underlying model. But this is a little weird because it doesn't really tell you anything about the structure that you discovered, the topics that you discovered. It just tells you how well you can predict this held out data. Does this mean that people don't care about what the topics are? I think the answer is pretty definitively no. If you look at any topic modeling paper, you'll see a chart that looks like this or this. And you see it even if you're not looking at English documents or if you're not looking at natural language at all. And you have these topics being displayed, one, because people think that they're cool and they show, hey, we're doing something neat and it makes sense. But people put so much faith in these things that they even use it to draw conclusions. And so there was this nice paper from 2008 that basically used the stuff that they discovered from topic models to prove that statistics is taking over computational linguistics.
And that's actually true, though.
One could argue it.
You are.
Yeah, right. And this is true even outside of academia. There are sites where you can go to. They use topic models to suggest things that you should be reading. JSTOR allows you to refine your searches using topic models. So this shows that somewhere people care about what the topics are. And what's a little dissatisfying is that they care about what the topics are, but when they go to evaluate their models, they don't really care about the model behind the curtain. And what you see is sort of this reading tea leaves approach. They stare at these topics long enough and it seems to make sense. And we call this sort of the reading tea leaves approach. And that's really unsatisfying. What would be nice is to have a direct quantitative evaluation of whether the topics that you discover make sense. And that's what I'll be proposing. Yes?
Yeah. So if you were to accept the Times' ability to divide things into fashion, sports, and so forth, and you were willing to live with 3 topics,
yeah,
you could test easily.
Right, exactly. And so that's one way to do it, but it's a little more granular, and there are differences of opinion. And so if another human being looked at the New York Times, they might slice it up differently. And in fact, people do slice it up differently. And that's basically what a topic model is doing. And so what we would like to do is ask a question, given the slicing, does it make sense to someone else that you bring in to have them look at it? And so it's a little bit different.
It seems like that's giving your model a little more room than if you ask whether it matched the dead editors at the New York Times.
Exactly. Yes, and I think that's true, but I think it's also fair because we could bring in you as the editor, and you might have something different, and we want to know if that makes sense as well. Yep.
I'd just like to back up a little bit and ask, what's the advantage to doing topic model when, as you described it, over, let's say, clustering?
No. And so 6 of one, half a dozen of another.
Yeah.
And so one could get into reasons why one might prefer one over the other. Mm-hmm. This seems to work there are ways to do this a little bit faster than traditional clustering methods, but there's really no big difference. Mm-hmm. And so with the standard k-means clustering or whatever, you would have similar problems. Mm-hmm. And so, and there's no sort of ground truth on what clusters should look like out of k-means clustering either. Okay. Right, and so what we'll do is we'll propose a measure of how much these topics make sense, and we'll test it out on different models in corpora, and we'll demonstrate that often what we're measuring isn't what we care about, using the traditional measures from the statistics and machine learning literature. Okay, so we want to have a measure of how much these topics make sense, and a measure that makes sense, at least to me, would have to be one that coincides with human judgment. And I don't think that there's any way of getting around asking people to say whether these models make sense or not. And so that's what we'll do. We'll ask people directly, and we'll do so in an experiment that is quick, doesn't take too much of their time, is not too onerous, and gives consistent results. So those are our goals. And so in order to do this, we're going to turn to a platform called Amazon Mechanical Turk. We're going to go out and give our assignments to Mechanical Turk. Mechanical Turk is an interface that then farms it out to hundreds of thousands of people around the world who get paid a couple pennies for doing each of our little tasks. And I'm going to talk about 2 tasks. One task we call word intrusion, and the other task we call topic intrusion. Questions so far? Okay, so normally in this place I used to have slides explaining what Mechanical Turk is, but I find that I don't need to do that anymore. But does anyone need a quick explanation of that?
No, I just want to say, if we built a Mechanical Turk to respond to your questions, how much money could we make off?
Yeah, probably not that much. Yeah, so this is a not too challenging experiment, and it isn't a Turing-complete task. Okay, so just as a reminder, we have these topics. Topics are, we can think of them as just a collection of words that somehow make sense together. And one thing we can do is we can ask how much a human is able to see the patterns in these words. So what we can do is we can take a topic. These words should presumably make sense together. Then take another word from a different topic that has high probability in that topic, and then stick it in there. And so if the original topic made sense, presumably the human is going to be able to consistently find the intruder word.
The more you give it.
What do you mean, the more you give it?
Well, if he only pig and apple, he obviously couldn't.
Right. Yes, and so with enough words from the original topic, yes. And so with one other word, it wouldn't make sense, but we're going to give them 8 words. And yeah, and so the hypothesis is if the topics made sense originally, they'll be able to find the intruder. Do you have a question?
Maybe.
Okay. All right.
I don't want to intrude too much.
Okay. All right. So this is what the task looks like. Each of these is a task. They click on the word that doesn't belong. We shuffled the order of the words. Which intruder we used was varied. And we modeled, we measured how often they were able to click on the true intruder. So, do you still have a question?
Why are you injecting an intruder rather than looking at just the consistency of the cluster itself to see if any words?
Right. Well, so this is an
clustered?
easier question to ask, and so click on the word that doesn't belong rather than wait how much you think these words belong together.
Well, yeah, but you could show all the words for a topic and then ask them if to select n words from that topic that don't seem to fit with the other
But there's not a
words. in
finite
the
number
topic.
of words.
Exactly. Yeah. Yeah.
Well,
There's,
work.
And it's
Yeah.
also, the more that you look at a list of words like that, the more possible connections between the words you see.
right. Exactly.
And so
Yeah, so
it
this
becomes
is getting-
really, really hard.
Getting back to the reading tea leaves aspect, if you stare at a list of words long enough, you can find as many fine-grained gradations as you want.
Is a topic accurately represented from its top 5 words, though?
Ah, well, yes, that's a question that I'm sort of sweeping under the rug, and so that's what everybody else does, and so that's what I'm doing here, and so that's
Is it
a
a good
perfect.
assumption to make, you think?
I don't know. I don't know what better thing you could do, and so other people weight it differently, like they do like TF-IDF reweighting, and there are many other things you could do. It doesn't change that much. You get slightly different results. I think broad strokes, it's roughly equivalent, but that's a very good point. Yeah.
You're basically showing people categories,
Yeah.
right? And it's been demonstrated that there are cultural differences in identifying categories, but you're sending this all around the world.
Yeah. Yeah.
Yeah.
And-
Do you find
and-
anything like that?
It's not so much cultural as knowledge specific. So we had great agreement on most of these topics, except the ones that were very New Jersey centric. and so people did okay on the New York ones.
Yeah.
I don't know why, but on the New Jersey topics, people did not do so well in terms of agreement. But it still was pretty good on average.
Are you allowing Turkers everywhere to do these, or are you limiting it geographically?
And fair
Everywhere.
game. Yeah.
Okay.
Okay, so that was task number 1. Task number 2 is doing the same thing, but on the association of documents to topics. And so here, what we have is we display a document in the first 500 words of the document. We show the 3 topics that had the highest weight associated with that document, and then we throw in another we throw in another topic, and we ask if they can pick out the intruding topic.
This is a Sesame Street problem.
Yes. One of these things is not like the other. Right. And yeah, so very simple. And then again, our hypothesis is if that the association between the document and the topic was wrong, then users will be able to consistently click on the intruding topic. Yep.
I mean, this is off the wall speculation, but suppose you just showed them the 4 topics without even showing them the document, and said one of these does not belong. That would give you a kind of baseline which is unrelated to how well the topics describe the document.
Right, yeah. I suspect that would not work so well. I suspect that it would get low results, but we didn't try that. But yeah, that's a good point. Okay, so this is what the task looks like. You see a little bit of the document. You can ask to see more if you need it, and then each of these rows represents a topic. And then they click on the topic that they think doesn't belong. Okay, so questions on the 2 tasks. Okay, so we tried this out on a number of topic models. I won't go into the details. Basically, we tried it out on an older model called PLSI, sort of a slightly newer, more rigorous model called LDA, and then a shiny new complicated model called correlated topic models. And the details are relatively unimportant, but what's important to note is that the newer things like correlated topic model, very expensive to compute, very complicated, but it does great when you ask it to predict words using the traditional perplexity measures. Yep.
Does the normal thing permit negative weights of a kind that wouldn't be allowed under LDA?
A little bit, yes. So you can have, so not negative weights per se, but you can have like anti-correlations and correlations. So like you can say these topics always go together, this topic doesn't go with this topic, that sort of thing. Okay, and we tried this out on 2 different corpora. One was Wikipedia, one was the New York Times. We chose these because they're relatively big. They're used by millions of people every day, so relevant. And the documents are structured well. So in a newspaper article or in a Wikipedia article, the beginning of the document should give you an idea of what the document is about. So this sort of helps us do the topic intrusion task a little bit more effectively. Oh, yes. And also these corpora have many different themes. And so we can get very heterogeneous topics out of them. Okay, so we applied these.
A number of times in the Times. Huh?
Yes. So we yeah. so we tried this out with a number of different models, with a number of topics, and we showed 50 topics for each condition to 8 workers, and we showed 100 documents from each condition to 8 workers again, and collected these results. And so now we can see what topics make sense. And so on the word intrusion task, this topic over here, artist, exhibition, gallery, museum, painting, did great. Everybody was able to click on the intruder. Nothing got by them. But this guy over here, committee, legislation, proposal, Republican, taxis, no matter what intruder word that people put in, they thought that taxis was the intruder word. And so this is a topic that did not make sense to people. So whatever intruder word you put in, whether it was fiberglass or whatever, people thought that that made more sense than taxis. Yep.
And taxis was the 1, 2, 3, 4, 5th
Yes.
heaviest word.
Mm-hmm. Yeah,
So if
and
you'd shown them only 4, it would have been cool.
yeah, exactly. Yeah, and but we did shuffle the words, and so it's not a strict ordering when they saw it. But yes, if we had a smaller set, it would have been okay. And we can also ask what documents had good associations to topics. And so the topic model was able to figure out that Lindy Hop was all about dance, and it was able to associate it strongly with the dance topic, and people agreed with that. But when it came to the Wikipedia article about book, Wikipedia didn't have a good topic that sort of encompassed what a book was about. And
But part of Wikipedia's worldview.
Right, exactly. That's a good point. And so the model was confused, so users were not able to pick out which of the topics didn't fit with book. And so here is an example of a bad association between the document and the topic. And we can also do the traditional evaluation. And we can ask each of these models to predict held out data, and the correlated topic model wins about half the time. In some cases, blowing away the competition pretty definitively. In the other cases, being pretty much the same. And so it's doing pretty well. But we can compare them against these human measures and these traditional measures. And so let's say that you needed to choose which model you were going to use, whether you're going to use the new shiny correlated topic model or something old and reliable like latent Dirichlet allocation. And so if you look at the held out log likelihood, you can choose which one you could use. Another question you might want to ask is how many topics do you want to use? So if you look at here, this graph, you have held out log likelihood on the x-axis and our model precision on the y-axis. And as you increase the number of topics, the likelihood improves. But as you increase the number of topics, the model precision decreases. And there's a statistically significant negative slope to all of these lines. And so as you increase the number of topics, the quality of your topics goes down, even though your precision keeps going up. And so the model is getting finer and finer gradations, but people are understanding less and less of what's going on. Okay, and you could also ask the question, hey, I don't know whether I should use correlated topic model or LDA, And so if you look at correlated topic model, it's blowing these other guys out of the water for especially for 100 topics and 150 topics, it's way out to the right. But if you look at how well the model is associating topics to documents, these old guys are doing quite a bit better on this topic association score. And so I think this is showing that there's a disconnect between how topic models are evaluated and how they're actually used by human beings. And I talked about a way of eliciting a way of evaluating an unsupervised model. And we showed that, at least for topic models, we could give a direct measure of the interpretability of these clusters. And so this is applicable to other models as well, so like k-means, like you mentioned. And to me, at least, this was a surprising result, that measures of perplexity that are sort of tried and true don't necessarily give you what you care about. And so the moral of this story is measure what you care about. And if you care about having models that are interpretable, to have topics that you would actually consider fit for human consumption, you should measure that and make sure you're doing a good job there, rather than turning to something like perplexity.
Question, you did something clever which wound up with a kind of negative finding.
Mm-hmm. Right, well, so the nice thing about this is that either way, it turns out well. Either there's a negative correlation, in which case perplexity is bad, or there's a positive correlation, in which case just use perplexity.
Okay, so in Act 2, are you going to give us a hint of how we could train for interpretability if we didn't have humans in the room?
Okay, so no, not exactly. So Act 2 is about, so here are some problems that can come up in topic modeling, and here we can diagnose the issue, and Act 2 is going to be the cure. And we still have humans in the loop. And so there are some things you could do without humans in the loop, but that's not exactly what I'll be talking about. Yep.
So I'm still not convinced that you're measuring what I care about.
Okay, all right.
In a user interface, I'm not convinced that listing a bag of words as a representation for a topic is a meaningful way to represent that topic to a person. So what are some alternatives that you might use to represent topics? Are there structured variations to topic labeling?
Yeah, and so they're all sort of post hoc measures, and so you can extract out salient bigrams. You can find phrases that correlate really highly with using TF-IDF or something. And so, yes, you're right. If you were making a really fancy interface, you would use something like that. For sort of purity reasons, we just wanted to use bag of words because we didn't want to have additional confounds. But yeah, you're absolutely right. Yep.
And so, are we really worried about interpretability all the time? I mean, the way it's one way it's used is for browsing collections and distance reading kind of thing. But the way I'm familiar with it is it's used as a set of features that's then fed into another process that then uses it. And then there I would think, well, the same with perplexity. It's the predictability. So if you have 100 topics that are in some way consistent, so they're not just, it doesn't just happen to be, you're not randomly splitting stuff. It really thinks that there are at least 100 topics that it can reproduce pretty consistently, then you'd want to use those. And there the perplexity, I would assume, does correlate with how well it will do in practice. I don't know.
Well, I would argue that perplexity, again, is not what you care about. You care about this other downstream task, and so you should just you should measure how well you're doing on that downstream task.
And has that been? I mean, are you familiar with results that have done that?
Stay tuned. We'll have some.
Okay, yeah, and yeah, so there are some examples. So like, for example, Dave Bly has his supervised LDA. And you can actually get better prediction results if you use that to change the likelihood function. Eric Xing has similar results using MED-LDA, and so yeah. So there, grafting on what you care about actually does improve this downstream task.
Right. Now, I'm just wondering if there's a correlation between what the interface people or the interpretability people care about and what the machine learning, just plug it into as another feature people care about.
Right. I think there is a bit of a disconnect there. Yeah.
Yeah. So I don't know if David has told you about this, but we are running and starting an experiment at the archive, where basically we're going to try switching in and out, LDA and other tricks. But like Sam was asking for, the bottom line is, are people getting documents that they want from this archival system? Right.
Yeah. And exactly. Nina had some great insights on how you might engineer a task where you'd actually do that.
I guess I'm going to ask, what do you care about when you're measuring like this, like you did?
Yeah.
What is the downstream task for which this is an appropriate measure?
Right, and I think the task is something like browsing a collection and displaying topics that make sense to people. Yep. And
I'm a little bit concerned about the comparison of different number of topics.
Yeah.
Because maybe it's not that fair to present the same number of words for each topic to the user, because then they're basically...
Right, and I think that's a valid point. And so here we're sort of examining the context of what you would actually show to people. And so if you're willing to accept that we're going to show n number of words to people no matter how many topics we're using, then this makes sense. But yeah, there are some issues here, like we have models with different number of parameters. We shouldn't be doing a direct perplexity comparison, so there are some issues there.
Well, I mean not in the perplexity analysis, but in the interpretability results.
Yeah.
When people
That's
see...
a good point.
Yeah.
If I'm seeing 5 words, only one of which is coming from 100 different topics.
Yeah, and so if you're willing to accept that we're going to show in words to people all the time. Yes, you've been very patient.
Yes. Are you measuring how your bags of topics or words are evolving across the time period? For instance, New Hampshire voters really matter for 2 months out of every 4 years.
Yeah. Right. So no, there has been some work looking at that to discover those, but not to analyze the interpretability of that.
Like a blip.
Yeah, exactly. But yeah, and so you do see those things, and so if you look at, so there is an elections topic that does come out, and then it peaks like October of every year, and then disappears, and is especially peaky every 4 years. So you can see those patterns, and that's one of the nice things that you can do with these sorts of models. Okay, all right, so now I talked about the problems. What can we do with them? So what can we do about them? All right, so why would you want to have an interactive model? And so what I'm going to be talking about is a model where you can correct obvious errors easily, where people can look at something and say, oh, that's absolutely wrong, that's not what I want. You can correct it easily and help build better intuitions in the user. And so if they can have an interactive model and they can fix things in it easily, that will give them a better idea of what's going on underneath the hood, rather than just having a big complicated black box that spits out an answer and take it or leave it. This also encourages buy-in, because if users are able to sculpt and shape the models into what they want, I think that it gives them a little bit more investment in what's going on. And I think that this also could lead to better downstream models, because you're able to quickly refine, prototype, and fail fast in your building these models. Okay, so what sort of problems come up in topic models? And so we talked a little bit about this, but let's get into a little bit more nitty-gritty detail here. So let's say you have 2 topics like this, and you show these to a user, and they say, oh, well, the shuttle launch and NASA really should be together. And because otherwise you get this sort of odd conflation of a sports-like topic that talks about shuttles and rackets, with the space topic. Another problem that you can see is that in this topic, this is on real data from the NIH. If you show this to someone at the NIH, they look at this and say, oh, well, there's really something going on here about the bladder and the urinary tract and that sort of thing. And there's also something going on with like the spinal cord and that sort of thing. And if you show this as a single topic to an NIH person, they think this is complete anathema. These things do not go together, and they get really upset. And this could cause them to just completely reject the entirety of the model based on this one problem. And so how can we fix these problems? And so in a normal topic model, the words are just distributions over words. And so they're completely flat. There's no correlation between the words. And so what we can do to fix it is introduce some correlations to address these problems. So if we want to add in these correlations, we could say that shuttle NASA space should have a positive correlation. If you see one, then the other words should have similar weight. And similarly, Constitution and President, those should also be positively correlated. And if we want to do something like fix the urinary and spinal correlation, we could put a negative correlation in between those guys and say, if you see bladder, spinal cord should have an opposite weight. Okay, and so I'm not going to go into the technical details. We can do this using something called a Dirichlet forest. This has some nice properties in that you can still do what's called conjugate inference. The details work out nicely. And
just one question about it.
Yep.
You won't go into the
Mm-hmm.
details. So it has the effect of causing the topics to have this kind of clumpiness or anti-clumpiness.
Mm-hmm.
Documents are still generated by randomly choose a topic randomly.
Yes. So the topic multinomial is still uncorrelated. And so for example, in the correlated topic model, they do impose this correlated structure on the document level. And here we're doing it in a more efficient way, but with a correlation structure over words instead. So there's a little bit of anti-symmetry there. Okay. Right, so in the interest of time, I'm going to skip over some of these details. Okay, so how do you incorporate this feedback? So the basic setup that we're working with is one where you fit an initial model, you then show it to a user, they tell you what's good, what's bad, what additional constraints do you need for this model to make sense to me. And then you replace the model with a correlated one. So you start out with an uncorrelated model, you get some feedback, that gives you a correlated model, you replace your initial model. But we want to do this in a way that keeps the computation fast and consistent. And so we're going to accomplish this by doing basically selective forgetting. And so someone playing devil's advocate might say, why not just start over? You have a model that had problems, why not just throw it away and replace it with this new model that hopefully fixes some of these problems? And so one reason that you wouldn't want to do that is that it results in a more expensive computation. That you're starting over completely from scratch, you're throwing away anything that you had before that you might want to build off of. Another reason is you might create more problems. So the user had a small little area of the space where they diagnose some problems, and you're just going to throw away everything and start over. More problems might arise that might have been okay before to the user. And lastly, it results in a bad user experience. As the user is inspecting this, they're sort of building a mental picture of what's going on inside the model. And if they think that, oh, topic 47, that's about politics, I like that one. And then you throw away everything that they learned about the model, there might well be another politics topic, but it could be 17 instead, and it might look a little bit different. And so if we're able to do it in a way that is incremental, we can sort of save on the computation, build a better user experience, and hopefully not introduce additional errors. And so in order to do this, we're viewing the problem as one of online inference. And so we have a model with some data, and basically what we're going to do is we're going to look at what the user tells us we screwed up on, then pretend that we never saw that before. We just forget it, wipe it out of our memory, and then start over pretending like we're seeing the documents for the very first time. Okay, questions?
I didn't understand what you just said.
Okay.
You're pretending you're seeing the documents for the very first time.
The
and
problem-
at the same time keeping.
Yeah, so we have a lot of documents, and the user is going to tell us where we screwed up. And so we'll forget those documents, but remember everything else for the other documents.
So the user is telling you about documents, not about topics.
Right, so this is something I haven't explained yet. I'll get to that shortly. And so there will be a number of ways that we can forget. Okay. All right, so in order to explain how we forget things selectively, I need to do a little bit of a discussion on how inference works in these sorts of models. It'll be very cartoony and hopefully not too painful. All right, so when you're doing these inference, basically what you need to decide is for every word in every document, what topic is associated with that word. So for example, we have this document, and every word we need to decide which topic goes with that word. So Hollywood might come from this artsy topic. So my studios download might come from this technology topic. Buy might come from this business topic. We go through here, and every word, minus the stop words, gets assigned a topic. So this represents the state of our inference, the state of our model at any given time. Okay, and so now we can pretend that this is a corpus. This is all of the documents that we have, and we have topic assignments. And so this is like we run inference in our model, and we're at some state. And this toy corpus has all of the problems that I talked about before in sort of the toy examples. And so NASA and shuttle are in different topics. That's wrong. We have spine together with bladder. That's also wrong. And so now we're going to try some different techniques of forgetting stuff to hopefully fix these problems, in addition to introducing these new correlations. All right, so let's say that we wanted to introduce negative correlation between spine and bladder. And so the user tells us bladder and spine can't be together. And so one idea for forgetting terms, forgetting is to forget the terms. So every time that you saw bladder or spine, you excise it from your corpus, you just pretend that it wasn't there. And now you pretend that you're seeing these terms for the very first time. And so now, when you do inference, you need to decide for each of these words what topic is going to be assigned. So let's say that you assign bladder to the yellow topic. And similarly, bladder also gets a yellow topic because within a document, you sort of want the same topics to be expressed. But now, when you get to this new document down here, you need to decide what topic spine is going to get. And you had this negative correlation between spine and bladder. So even if it wanted to put these guys in the same topic, this negative correlation would say, no, you shouldn't really do that. And so now, this guy will be assigned a different topic, now that this correlation has been introduced. Before, there was nothing pushing it to prevent that from happening. Okay, so now let's say that we want NASA and shuttle to be together in the same topic with a positive correlation. So idea number 2 for forgetting is to forget the documents where any of these terms appear. And so this is sort of going a little step further. So every time we have a document that had either of those words, we pretend that that didn't exist before and we're seeing it for the very first time. And so now we need to assign a topic for NASA. Let's say that that becomes blue. Shuttle, also blue. It's in the same document. We want the documents to have consistent topics. And then launch for the same reason becomes blue. And then when you get to doc 2, you can do whatever you want. And Racket, Serve, Shuttle, they can have different topics. But NASA and Shuttle all have the same topic. And so when you're choosing the topic assignment for this guy, you'll prefer blue because NASA already got some blue. But for another topic, you can choose to put shuttle in there, and if there's any other NASA that also fits in this red context, it might well put that in there as well.
Is this going to tend to make Racket want to line up with NASA too?
So to a slight effect, yes, but in topics where you don't have NASA appearing, it will be agnostic about what to do with shuttle.
Yeah, suppose you saw, you said, okay, you already saw Doc 1, now you see Doc 2, and therefore shuttle is already associated with NASA. Okay, what happens if you see Doc 2 first?
Right, well, so...
does it, then you...
Right, so if you see Doc 2 first, then you'll, let's say that you assign these guys all to one topic. And so now when you're over here, you need to make a decision on what to assign these guys. And so given that you haven't seen this document before, this document doesn't push you in any particular way in terms of what topics to use. And when you're choosing among all the different topics, once you hit NASA, that will fall into some topic. And so NASA, whatever topic NASA is in, will likely have a higher probability for shuttle now. And so whatever NASA got, shuttle will be higher. And so it doesn't really matter, given that this document has NASA. Other questions? Okay. So, so here's sort of an example of how you might use this. So let's say that you fit a topic model to the New York Times, and here's 20 topics. We cut some out for presentation. And so there's one topic that's all about Russia, the Russian Federation. And there's one topic that seems to be all about the Soviet Union. And someone looking at this might say, well, they're really part of the same narrative. This doesn't really make sense to me. And so you could put in this positive correlation that says all of these words, Boris, Yeltsin, Mikhail Gorbachev, Russian, Soviet, they should all be together. And so if you do that, and then use the doc strategy for forgetting, topic 20 then becomes something that's about both the Russian Federation and the Soviet Union. Topic 1 now looks like democratic movements in general. So you sort of had this democratic movements in Russia, and elsewhere you subtract out the Russia, and that just gives you democratic movements. And when you look at the other topics, they haven't changed all that much. And so this is accomplishing our goals of only changing what we thought was wrong. Okay. So another thing that we did was we simulated an interactive user. And we simulated this user by taking the 20 newsgroups corpus and extracting out what the constraints might be for a user that wants to reconstruct these newsgroups. And so we train up a classifier, and based on the topic assignments in a training set, and then ask how well it can predict topic assignments, predict the classification to these categories on a test set. And so presumably, if the model does better in predicting these 20 newsgroup labels, then the model underneath was more accurate, was closer to the truth. And so as we add these features, hopefully the error rate of classification will go down as this simulated interactive user makes more and more headway. We'll build a better classifier. Does everybody understand the setup?
No, I don't really know what you mean by simulated user.
Oh, okay. Well, so basically you can take 20 newsgroups, and for each of the newsgroups, you can, on a test set, you can extract out what words make sense for that. So like we're doing the information gain. So we're computing the information gain between all of the various feature words and the various newsgroups. And so for example, for soc.religion.christian, you get Catholic, Scripture, Resurrection, Pope, Sabbath, Spiritual, Pray, Divine, Doctrine, Orthodox. And so we're going to simulate a user that is building constraints with these words one at a time. So you start out with a constraint that says Catholic and Scripture should be together, and then they'll add in resurrection, and then the Pope, and then the Sabbath and spiritual, and so on. And so this really isn't interactive in that they're always doing the same thing. They're not looking at the models at all, but it's just sort of showing what happens when we forget with our various strategies.
So
Yeah.
It only adds positive correlation.
Yes. So yes, we're only doing positive correlations for this study. And so so we compare against not adding any constraints with starting over from scratch, and our various forgetting strategies, and we see that the doc forgetting strategy seems to work the best. There are other strategies we could try, but of the ones that we tried, doc seems to work the best, and it works better than the naive baselines. So another thing that we did is we put this out in the wild and asked people on Mechanical Turk to look at topic models and to go crazy. And this is just sort of more of an exploratory thing to see what would happen. And so we built an interface that they could select constraints, put them in, and then it would churn on the model and then spit something else out. And so they could delete links, they could add new links, and then there was another button they could hit to rerun the model. And I'll skip the quantitative results and go to the more interesting qualitative results. And so some of the constraints, because this is Mechanical Turk, were inscrutable. People were just clicking on things randomly. Some things were really interesting. So some people put in collocations like Jesus and Christ, solar sun. Those made sense. Other collocations didn't make so much sense, like even in number, book list. These things might not even be occurring in the corpus. And so that was interesting. And I think that there are some simple things that you could do to sort of correct these problems, like doing better bigram pre-processing. Another interesting thing that people did was they put in common instances of things. So like countries, they grouped them all together, and they put all first names together. And even though the model wasn't prepared for that, after somebody put in a first names constraint, it discovered a new topic about obituaries. And so people were able to sort of move the model into places that the model wasn't originally going to go. Another interesting thing that happened was that one user tried very, very hard to put Mac and Windows into the same cluster. And at least for the 90s, the model was not prepared to recognize that Mac and Windows should be in the same topic, and they kept them, and the model kept it separate because that better predicted the data. And so the people who wrote about Mac were using quite a bit different vocabulary than the people writing about Windows. So it shows that the user is not an absolute arbiter of what's happening in the setup. All right, so one things that we'd like to look at in the future to speed this up further. It's relatively fast. We're proud of that, but in an interactive setting, every second counts, and so we could really stand to make it as fast as we possibly could. We'd also like to incorporate other domain knowledge. Right now, we're basically starting from zero knowledge, and there are things like WordNet and the gene ontology that we could use to sort of bootstrap the process to sort of give the user some place to start, other than just completely an uninformative prior. We'd also like to do more interactive components, like making the vocabulary interactive, adding bigrams, nuking words, that sort of thing. And we'd also like to try this out on other domains, like applying it to images. There's been a lot of neat work using topic modeling for computer vision. And just to wrap up, I talked about a way for individuals to explore text in a way that makes sense to them, and to fix models so that they are actually interpretable and useful. And we're creating tools that allow you to do this, but we do need users. So if you have interesting corpora or applications, please do talk to me, and maybe we can set something up. Okay, I'd like to finish by thanking people whom I worked with and people who gave us money and data. And that's it. Thank you. And thank you very much for making this interactive. I really enjoy those sorts of talks more than...
You talk about interactive topic more.
Yeah, yeah.
We're very interactive.
Indeed.
What is the ARL project?
Right, so this is looking at creating models that can apply across languages. And so, for example, you're doing topic modeling in English and Arabic, and presumably if you have knowledge about how those languages fit together, you can have a better model of both things rather than doing either in isolation. Yep.
You mentioned speed as an issue.
Mm-hmm.
What are we talking here? Does this take like a minute to compute or a second? Or
yeah, well, it's more like 45 seconds for the New York Times. And so that can try some people's patience.
Mm-hmm.
Can you thin the data that it works with and speed it up?
Yeah, but that's always risky. And so I think we've done that as much as we care to do. And so we've already tried doing that.
It's parallelizable?
So we're doing GIB sampling, so it's not easily parallelizable. If we were doing variational inference, that would parallelize a little bit better.
Do you skip 100 steps and stuff like that?
Yeah. And so, and so if we were doing variational inference, it would parallelize better, but then you have to worry about latency if you're farming out to multiple computers, and so I think that what we want to look at is making the algorithms clever so that it will run as fast as possible on a relatively beefy multi-core machine. Yep.
Can this be used with or in order to enhance visual thesaurus, let's say?
Yeah.
I think, starting out with the best visual thesaurus available, then having your ideas kind of enhance it over time, and the interactivity coming in, and other like the less algorithm and similar tools to really keep on improving and updating the thesaurus semi-automatically, interactively.
Yeah, and I didn't mention this, but one of the things that inspired this work was using WordNet as a source of constraints. Mm-hmm. And so that's...
So it works together.
Yeah, and so that inspired it. And so just because that's a little bit more complicated, we didn't do the interactive part there, but that's something I'd be really interested in doing.
Any more questions? Well, thanks, Jordan. Again.
Okay, and thank you again for having me.
Please stay for the reception. We have a reception outside, food, and so we'll come to talk more with Jordan. It's mine.